Now we're going to look at the reciprocal of the cosine function. This is called the secant. So we can generate this as secx within the graphical calculator. And you can see that it's very similar to the cosecant, that is the 1 upon sine. It's just shifted by a factor of pi by 2. Now if we were to zoom in, this has been generated from minus pi 2 pi to 2 pi. So we will regenerate this within our CPU and try and get an image that looks just like this. So again, this function is going to be periodic over 2 pi. So we can take everything less than 0 and map it into 0 to 2 pi, and we can take everything that's greater than 2 pi and again map this into 0 to 2 pi. Now within the 4 quadrants, you can see the 0 to pi by 2 quadrant here, and then we're going to have the second quadrant here, the third quadrant, and then the fourth quadrant. So we can again fold the quadrants 2, 3 and quadrants 4 back into quadrant 1. So that in the end, the full domain of values is going to be folded into just 0 to pi by 2, and it will only be the 0 to pi by 2 that will actually go into the core of the chordic unit. Now again, let's look at some of the mathematics. We want to fold any angle into the secant core. By the secant core, what we mean is we want to take any angle and we want to eventually put it into the 0 to pi by 2. And it's only the angles from 0 to pi by 2 that go into the core of our chordic unit. So we're interested in the secant, which is 1 upon the cosine, and we want it to work for any real value of x. And we know that the chordic unit will work between minus pi by 2 to pi by 2, but we only really need the 0 to pi by 2. So we're going to take everything that's less than 0 and we're going to put it into 0 to pi by 2. Again, everything that's greater than 2 pi, and we'll put that again into 0 to pi by 2. And then we're going to go through this mapping. So x is the input angle, so it's the full domain, and we're going to map it into the reference angle alpha, which is 0 to pi by 2. And we're also then going to have to adjust the sign of this as well, from +1 to -1. So the first thing that we're doing here is the periodicity. So we're going to do the wrapping. So this is the first part of it, and in effect it's going to be an x modulo 2 pi. So everything out with 2 pi gets mapped into 2 pi. So once we've done the modulo 2 pi, we're then going to wrap the quadrants 2, 3 and 4 into quadrant 1, and we're going to use the values here in order to do it. So I'm not going to talk through these. It's similar to the reciprocal of the sine, and you can have a wee look, and if you want you can always regenerate these in Desmos and you can see how they work. So this is how we're going to perform the mapping, and this is really at the heart of our folding code. Now, as we've seen with the reciprocal of the sine, the reciprocal of the cosine is going to have an asymptote, but the asymptote in this instance is going to occur at pi by 2. So it's going to come from pi by 2 from the minus side, and then it's going to tend towards infinity. So you can see here, as alpha tends to pi by 2 from the minus sign, our sec x is going to tend towards infinity. So that's just where we've got our asymptote. And again, we're going to deal with it in terms of a value of alpha, and we're going to ensure that the value of our deal with it in terms of our value, epsilon, and we're going to ensure that the value of alpha doesn't go beyond the maximum value that we could get for our secant, which in our 16-bit floating point number system is somewhere around about 65,356, something round about that. And you can see that within the code. Now, if we head into the floating point library, and if we head down to the fold underscore C-sec, so that stands for the chordic and the secant, which is 5570. Okay, so we can go Control F and we'll put in 5570. Press return, and this is the folding function. Now again, we're not going to talk through all of the details. It follows the same as all the rest of the folding functions that we've seen so far in the course. Okay, so you'll be able to have a read through that, and if we head down, we should be able to see the point at which it heads off to, there we go, the maximum value, which is 65,504 for a 16-bit floating point machine. Okay, now the details of this don't really matter for us just now. What we're really interested in this part of the course aren't these details. We're interested in where this code goes and how we get access to the code, and how we're able to use this code within our assembly language programs in order to generate all of the values. So the individual details, or the minutiae of details here, are not necessarily important for the understanding of the whole of the course, but if you are interested, you can always go in and you can mess about with it and have a look yourself. Okay, now we can go ahead and we can open up the file. It's called chordic underscore, now it should be sec, so let's see if we can find it. There it is there, chordic underscore sec, so that's secant and it's full, meaning we're going to use the full domain. So again, this is the same as the previous file. The only difference is that we're now jumping to the subroutine secant underscore full in order to generate the folding for the secant, and then we're going to use the actual secant value within this jump to subroutine. And then we're going to do the plotting as well for all of the points. So we can go terminal, run task, assemble file, and then we can go terminal, run task, emulate file, now once the emulator has ran up, we can type the R for run and then the GD for the graphics dump. So now we're in a position where we can go in and we can load in the splash program into the RAM, and then we can load up the graphics display. So we'll clear this off and we'll load in the new .dat file. So if we head up here, there it is, graphics.dat. We'll close this down and now we can run the program. So that's it starting to generate the points now. So I'll leave that and I'll let it run, and I'll fast forward it to the end of the simulation. So that's us generated the secant function from minus 2 pi to 2 pi, and the 0 point is just lying along the axis here. So again, let's go ahead and we'll see how this actually looks once we've ran it on the RTM16. So this is the secant function rendering on the machine. Now it's still running through the last few points, so there's going to be a few points appearing just down along this section here. But as you see, it's looking quite healthy. So in the next video, we will go on and look at the reciprocal of the tan function called the cotangent. So thank you for listening. I'll get you on the next video. Goodbye.